What is Faraday Law of Electromagnetic Induction? I am writing it EMI. Okay, it is very important topic. So, what does it tell? You see, before looking at this figure, let us. I told you. I show you one thing. Suppose we are having one coil like this. We are having one coil like this. Okay, one coil like this. I replace change the coil. Okay, now we are having one coil like this. Okay, one galvanometer is connected here because galvanometer measures very small current also. It measures very small fluctuations also. That's why we are using here galvanometer. If suppose we are moving a magnet, maybe north pole or south pole, any towards the coil, what will happen? We know that from a north pole or south pole, we know that from north pole magnetic field comes out. That we know that magnetic field comes out. If suppose we are moving magnetic field, we are moving a magnet like this in this direction, what will happen? What will happen? The flux will change because we know that initially you see here how many flux lines, magnetic field lines are inside the coil. See, only two coils, only two field lines. But if suppose the magnet comes very closer to it, what will happen? All the four lines will come inside the coil. Then what we can say? We will say that with the movement of this magnet, we can say that magnetic field is changing. If magnetic field is changing, that means inductive flux is changing. That is the flux law. That is the Faraday law. What does it tell? It tells that the flux changing. The flux changing, whenever there is a flux changing between any coil, linkage, the flux changing with the coil, okay, then what happened in resultant to it, there is one EMF is induced in a coil. Okay, it tells, I tell you one more thing, flux linkage. Okay, what is flux linkage? It is, see here, how many field lines are linking with it? Initially only two lines. When this magnet will come closer to it, what will happen? All the four lines will come inside it. That means the flux linkage is increasing. Okay, because magnetic field lines are increasing, so we can say flux linkage is increasing. So Faraday law tells that whenever there is a flux, then whenever there is a change in magnetic flux linkage, then a EMF induced is in a coil, and that EMF induced E is given by change of magnetic flux, rate of change of magnetic flux. This is called as Faraday's law. What is Faraday's law? Faraday's law tells that the EMF induced in a coil is directly proportional to what rate of change of magnetic flux. Okay, for one coil. If we are having n coils, then what we will do? We will multiply a factor of n for an n coil. That's it. This is called as Faraday's law. Okay. Now, it is not a complete. It was not a complete because Faraday only told about the magnitude. You see here, only told about the magnitude. But since we know that, we also need direction. What will be the direction of the induced EMF? Because we know for induced EMF, polarity is positive and negative. So we need a direction also. So to define the direction, Faraday's law was not complete, and later on another law came, that was Lenz law. I will discuss it in further slide, but till now we are only discussing about Faraday's law. Okay, what was Faraday's law? I repeat it once more. Whenever the flux linkage with the coil is changing, how the flux linkage will change? Flux linkage will change. We know that it is depending upon B into A. Flux linkage will change by changing magnetic field or by changing the area. Maybe I change the area of this loop, make it bigger or smaller, like this. I make it bigger, then smaller, then bigger, then smaller. I can change the area also, I can change the field also. Whenever I change these two factors, I will see that the phi will change and also area between them. Okay, if the flux linkage will change, then EMF will induce in this coil, and the EMF induced will be dependent upon How much? N into d phi by dt. This was the Faraday's law. Okay. Any problem till now? Any problem till now in understanding Faraday's law? Now, let me tell you, if you understood the Faraday's law, then there was one problem. To find the direction later on, what happened? The lens came into the picture, and it told that since energy conservation. One more thing you should remember. One more thing, that if suppose I am moving the magnet, then how does, if I am just moving the magnet, how does a current or a EMF can be induced in this coil? One question arises, because we know in nature energy is conserved, it can't be produced. That means if we are just moving the magnet and changing the flux, how, from where did the current is coming, or EMF is coming to this coil? So Lynch told that the EMF induced in this coil is opposite to the polarity of the source which is producing it. It will tries to oppose the source which is producing. That means, let me tell you one more thing. How does the lens decided the direction of the current? Let me take one plain slide. I will explain from here. See here. What will happen? If suppose I am bringing North Pole closer to this magnet, when North Pole is coming closer to this magnet, what will happen? The magnetic field will increase in this direction. What will happen? Magnetic field will increase in this direction. What will happen? What will happen? That the current will, we know that the current will get induced, because we know if EMF is induced and a circuit is closed, loop is closed, then current will flow. So current will flow in this circuit. What will be the direction of current then? So Lynch told that direction of the current, induced current, will be that such that the magnetic field produced due to that induced current will be opposite to the original magnetic field. Original magnetic field was in this direction. It was initial magnetic field. So current will induce in this direction. Suppose I am telling that like this. See here, it is upside and it is down. Okay, what will happen? Current will flow like this. See here, current will flow in this direction. This will be induced current. See here. Okay. What is happening? Yes. Okay. This will be the induced current. What is happening? Okay. This will be the direction of induced current. Wait. Something stuck. Okay, now see, this will be the direction of induced current. This will be the direction of induced current. How we decided this? Lynch told that if suppose it is upside, you curl your forefinger in this direction. This is upside. You will see that for this induced current, the induced magnetic field due to this current, this will be the magnetic field due to induced current. We can write like this. And this magnetic field, suppose B dash, it will be in opposite direction to the initial magnetic field. You got it? How we decide direction? Got it? Or still have any confusion? I will take one more example then. Getting confused? Okay, let me take one more example. Okay. Suppose it is up, it is down. Okay. And what we are doing, we are moving north pole, north of this magnet, backside, like this. We are moving north pole of this magnet backside. What will happen? We know that suppose initially magnetic field was like this, linking with like this. Okay. Initially it was like this. But what we are doing, we are bringing it back. What will happen? We know that if we are bringing back, what will happen? We know that magnetic flux will decrease, linking with this coil. Then what will happen? The current in this coil will produce in that direction, which will support this magnetic field, because we know it will oppose. We know that the factor which is producing here current, it will oppose the cause which is producing. That means if the field is decreasing, flux is decreasing, then this induced current will try to increase the flux. If flux is increasing, then it will try to decrease it. See here, flux is decreasing, then what will happen? Since the flux is decreasing here, because it is going back, flux is decreasing, what will happen? What will happen? Here current will produce in such a way that the magnetic field will be in this direction only, so that it will support it. Okay, how will the current flow? How will the current flow? Current will flow in this direction, so that you curl your four fingers, you will see that your magnetic field will point in this direction only. So it will support the original magnetic field, because it is decreasing, so it will try to help it increase it. And if it was decreasing, suppose, I think you're not getting clear picture. See here, I tell you one more example. Take one more example. I know, I'm feeling that only. Yes, we know South Pole. Like this, suppose we are bringing South Pole toward the coil. What will happen? See, if we are bringing the South Pole toward the coil, what will happen? What will happen? If we are bringing toward the coil, we can see that magnetic field flux linkage with the coil is increasing, and the magnetic field is direction this, and it is increasing. You see here, field direction is this, initial direction is this, and it is increasing. So current will induce, and it is up and it is down. Okay, current will flow in this direction such that since it is increasing, it will try to decrease it. So current will flow in that direction such that to decrease it, current will flow in that direction such that its magnetic field is in this direction, so that it will oppose it. So where will be the current direction? It will be in this direction, so that its field is in this direction and it opposes the initial field. Okay, got it, or have any problem? Please tell, please tell. If you are facing problem, I will take one more example. Let me take one more example. Okay, you got it. That's it. That's it. I want to explain that only. Good. Good. Oh, if you got it, then please tell me one more. I would like to give you one question. If you got it, very good. I would like to give you one question. Yes, I would like to give you one question. Suppose I am having one coil. I am representing it like this line. If suppose I am bringing South Pole away from it, what will be the, this is coil is like this. Okay, you have to tell here dot or here cross or here cross or here dot, like this. I want to answer in this term, in this one, right one. Dot or cross, you tell. South Pole going backward, what will happen in this coil? Dot or cross here in this one. Let us suppose A and B. In A part, what will happen? Dot or cross? Dot means current will come from here and go inside. Can you tell me what will the direction of current in the A section, like this? Can you tell me? Can you tell me? Please tell. This answer came in. Okay, let me check it. Let me check it. You are telling inside. Oh, one more thing, that South Pole means current magnetic field like this, and you are what happened now? And you are moving it downward. That means flux linkage is decreasing. That means we can say flux is decreasing, so it will try to produce current magnetic field in this direction only. In this direction, so we support it. Okay, so it will try to produce in this direction only. So current will flow how? I think here it will be dot and here it will be cross. You see here, so that current, so that field is in this direction only. because it will try to support it. Got it or have any problem? I think you tell in the opposite sex. Got it or have any problem? Confusing? Got confused here? Any confusion, or I should explain once more? Subtle in the loop form. Okay. No. You should explain. You should think like this also, because sometimes question can come like this also. Okay. I will take in loop also. You see. I take it like this. Okay. You see here. If suppose it was A, it was B, and suppose it is up and it is down. Okay, up and down. Okay, now what will happen? I am telling that south pole is going back. What will happen? We know south pole magnetic field is in this direction. South pole going back. That means flux is decreasing. So this coil will produce its induced current in that direction, such that it will support the magnetic field, because it is decreasing. So it will support it. That means the induced EMF, the induced current magnetic field will be in this direction only, so that it will support it. So we know to have in this direction, how will the current flow? Curl your four fingers. You will see that it will flow in this direction only. If it is up, okay, then it will flow in this direction. I think it is up, then I think it will flow in this direction. See here, curl your four fingers, it is up. You see here, so that your thumb is pointing in this direction. Yes, we got it. Yes, you got this here. You see here, at the point A, current is coming outward. You see here, current is coming outward. And at the B, this current is going downward. I have shown this section in figure. You see here, this section in figure. So current is increasing up. In A, it is dot, and in B, it will be cross. You see here, you can relate it. Okay. Got it till now? So, how did you choose that, sir? Not getting your question. How choose that? What you're telling, I'm not getting. Actually, what is happening? Lenz law tells that if flux is decreasing, induced original flux is decreasing, okay, it will try to increase it. If field is decreasing, it will try to increase it. If field is increasing, then it will try to decrease it. Okay, it will try to oppose the cause which is producing it. Okay, if it decrease, then it will increase. If it will increase, then it will decrease. Okay, that concept I have used here. Okay. I think some mistake occurred. What happened? Any problem till now? Now, this was the Lenz law. Now, we can write it in complete form. E is equal to minus n d phi by dt, and this minus sign came due to Lenz law. This negative sign came due to Lenz law. And we can, one more important point, we should know that Lenz law is based on energy conservation.